I'm getting all of these Zoom notifications, aren't I? That show when people enter. Maybe I can turn that off. Let's see if I know how iPads work. Maybe this will work.
I'm going to begin, or you're going to begin. I'm going to start introducing you. Hi, everyone. Welcome back, and thank you for coming today to the categorification seminar, and thank you for joining us at this slightly off hour today. We are lucky enough to have Anna Romanova from the University of Sydney telling us about a tour via examples of Beilinson-Bernstein localization. So she's speaking today, and then we will actually have her back about a month later to tell us a little bit more about how this is actually going to be used in categorification. So, you know, come back in a month and listen to more of it and come back next week. Anyway, thank you, Anna. It's all on you.
Great, thanks, Nicole. And thanks for having me here. I'm really excited to be able to give a seminar from across the ocean. This is one of the silver linings of this strange online time, is that now those of us who are far away in Australia can talk to the rest of the world much more easily. So my talk today is called A Tour via Examples of Beilinson-Bernstein Localization. And mainly what I want to do today is I want to tell you about what I think is a very beautiful theorem. So here's a shot of this theorem as it first appeared in French in a 4-page paper in 1981. And this little theorem in this little paper went on to change the course of representation theory. And so this is what I would like to tell you about today, because I think that it's a really beautiful story, and I think that it's a really beautiful theorem. So, of course, I will get into a lot more detail. This will not be the only time that I'll show you this theorem today, but this is the first time that I'll show it to you. And so my plan for this talk is that I want to spend some portion of it telling you why I find this theorem so beautiful. And this will amount to a bit of history that perhaps you've heard before. And then I want to tell you very briefly about how it shapes my own mathematical world and the way that I think about problems and what I study. And then the main part of my talk, what I want to get to, are lots and lots of examples. So examples showed up in the title. This is supposed to be the purpose of this talk, is to show you many, many pictures of D modules and convince you that they're nice objects to work with. Oh, I had this all planned, and let's see what happens. So, but I do have to start with an apology, which is that this is a categorification learning seminar, and this is not a talk about categorification. But my one caveat is that, as Nicole said, I'll be speaking again in October. And in October, I'll give a talk where categorification does show up, and also a little bit of Beilinson-Bernstein localization as well. So if you are itching for some categorification, then hang tight, and in October, we'll get a little more of it. Okay, so let's get going, or I actually start writing now. So why is it that I find this theorem so beautiful? So to tell you this, I'm going to tell you some history, and this is quite classical history, and so it's very likely that you have heard this story before. And so if this is a very familiar and boring story to you, I just ask that you bear with me for a bit, because it's necessary to set the scene. So we're in the 1970s now, and at this point in time, there was a collection of people who were interested in studying the representation theory of semisimple Lie algebras that are complex. And underlying this, there was sort of a question hanging about, which is it possible, let's try eventually I'll get the hang of this, to classify all representations of some Lie algebra? Because maybe we have some object in mathematics that we care about, and so a natural, in this case, the representations of some object, some Lie algebra, and a natural question is if we can classify them. Can we write down a nice way to describe all of them? And this started out well. If the natural starting place for classifying representations are finite-dimensional ones. So if we want to classify finite-dimensional representations of a complex semisimple Lie algebra, there's a really beautiful classification by the theorem of the highest weight. So simple finite-dimensional G modules, representations of the Lie algebra, are in bijection with dominant integral weights. Great, so this was a simple and satisfying classification for finite dimensional representations. And for example, in SL2, which we'll focus on in the rest of this talk, this is just saying that for every choice of a positive integer, we have a unique irreducible representation of that dimension. And so in this classification, along the way, some other representations show up. So along the way, Verma modules show up. And these are infinite dimensional representations, but they have the nice property that we can describe all of these finite dimensional simple representations as unique quotients of Verma modules. And these are infinite dimensional, but they're very nice. They're highest weight modules. They have a very orderly structure, and they make sense for any choice of lambda. It doesn't have to be dominant integral. And so this gives us a new class of modules. Sometimes they're irreducible. And so a natural place to study both of these finite dimensional modules and the nice orderly Verma modules is category O. So a natural ambient home for both is this category of representations called category O. And in this category, it breaks up into blocks, which are determined by the action of the center of the universal enveloping algebra. And each of these blocks has a nice structure. So if we wanted to study this category, we would ask about what the structure of one of these pieces is. And if we look at the growth entity group of this block of category O, this has two natural bases. It has one given by the collection of simples, and it has one given by the collection of Vermas. So in our discovery of these classes of representations, the next question we might ask, we have some category, we can describe two classes of objects in that category. Each one forms a basis for its growth entity group, so each one kind of describes the underlying combinatorial skeleton. So a natural question is how they're related. So what's the change of basis matrix between these two bases? And this turned out to be hard. So this question was a hard question, but there was a conjecture put forth in 1979 by Kazhdan-Lusztig that this change of basis matrix was given by a set of recursively defined polynomials that were defined in terms of the Hecke algebra of the associated Coxeter system. So these are some collection of polynomials that depend only on the Weil group of the Lie algebra that we started with. And the conjecture was that these polynomials completely described the change of basis matrix in this block of category O. Okay, so now our story continues. And this is the point in the story where geometry enters. So in 1981, Beilinson and Bernstein built a bridge. And their bridge was between representations of our Lie algebra with some fixed infinitesimal character, which I'll call chi lambda. So this is just saying that the center of the universal enveloping algebra acts by scalars on these representations, that there was an equivalence of categories between these and some other objects called d lambda modules on the associated flag variety. So this is an equivalence of categories, and it was also very explicit. So what they said is these d lambda modules, which look, so d lambda here is a twisted sheaf of differential operators. So locally this looks like a sheaf of differential operators, but there's some twist in how it's glued together. And what they showed is that if we take any of these d modules on the flag variety and we take its global sections, that this naturally has the structure of a representation of the Lie algebra. And they also gave a functor going the other direction. They gave some process for starting with a representation of the Lie algebra and doing what's called localization to construct a D module on the associated flag variety. So on this side of the equivalence, we have some objects in representation theory, representations of Lie algebras. And on this side, we have some objects in algebraic geometry. So what this theorem did is it provided a bridge between representation theory and algebraic geometry. But was it actually helpful? So why did they do this? Was this a helpful bridge? Well, it was. And this is because when we move things to the algebraic geometry, there's some strong tools. And one in particular is the decomposition theorem. And this is some theorem that tells us what happens if we take a simple object and push it forward through a proper map, and what we get ends up being semi-simple. And it turns out that this fact is very useful. And so this is some tool that we have on the algebraic geometry side that we don't have an equivalent of on the representation theory side. So this theorem entered the picture, and the reason why it entered the picture was to prove the Kazhdan-Lusztig conjectures of 2 years earlier. So Beilinson and Bernstein, they used this bridge to prove the Kazhdan-Lusztig conjecture. And they could do this because if we look within the category of G representations with some fixed infinitesimal character, within this is the block of category O that showed up earlier. And so we could figure out what d lambda modules on G mod B correspond to the representations in category O. And they showed that these are the ones that admit an N equivariant structure. So we could describe category O geometrically using this certain class of D modules. And this gave them enough tools to prove Kazhdan-Lusztig's conjecture. So it's of note here that they introduced the theorem to prove something about category O, but the theorem is much broader. It applies to essentially all representations of G. The only restriction we have on the left-hand side here is that we have a fixed infinitesimal character. So what this theorem did is it brought about a new era in representation theory for a few reasons. One is that it provided a whole new powerful set of tools. And for a while, it seemed like these tools were actually necessary. For example, for a long time, there wasn't actually an algebraic proof of the Kazhdan-Lusztig conjectures until 2015 with Elias Williamson. So it seemed at first like these geometric tools were necessary in our understanding of representation theory. But I think more interesting than this is that it demonstrated that we were asking the wrong questions to begin with. So it demonstrated that our initial question, which was the question of can we classify all representations of a Lie algebra, was misguided. And why is this? Well, once we realize that representations of Lie algebras are the same as D modules on flag varieties, we can see that there's no hope of classifying those. There's no hope of classifying all D modules in some reasonable way. And let me give you an example to try to convince you why this is true. So take, for example, SL2. This is what we're going to get to later in the talk. But if we look at SL2 modules for SL2C with trivial infinitesimal character, we'll see many more details of these later, but these correspond under Beilinson-Bernstein's theorem to D modules on P1. And so P1, I'm going to think of for the purposes of this talk as a sphere. And so I could take a sphere and I could subtract a bunch of points. So say I have P1 minus 34 points. Then if I looked at the fundamental group of P1 minus 34 points, this is isomorphic to a free group on 33 letters. And representations of this fundamental group, for every representation, I can cook up a D module. So representations of this give dp1 modules. And I won't tell you exactly how this goes, but essentially I can choose the monodromy around each of these points. And from this, I can build a D module. So for every representation of the free group, I can build a D module. So what this is telling us is that the representation theory of all free groups is contained in the representation theory of SL2C. So this shows us that the question we were asking is unreasonable, because we're not going to be able to, like, there's no relations in free groups. If we're studying the representation theory, it could be anything. And so trying to classify all D modules in some reasonable way is just not really a question we can answer. And so because of this was a major turning point in the field. It fundamentally changed the way that we were thinking about questions in representation theory. And the new approach was that we are no longer looking at classification questions. We can abandon questions about classification and instead focus on representations that have some sort of significance. And then we can look to geometry for intuition as to how to understand these representations.
And
okay, so that's, yeah.
So, okay, so you were saying that for each such representation, you can construct a D module. Is it obvious that different representations give forth different D modules? I mean, like, or they're not isomorphic? How do you know that maybe you're not getting 100 million, but they're all secretly the same? Like, is that?
Yeah, great question. It's not obvious because I haven't told you how to construct this at all, but it's true that for every representation, you'll get a different D module.
Okay. There's no easy way of like one-lining, explaining, or motivating.
Oh, so what we should think about is that we're choosing like a monodromy around each of these points. So if we zoom in on one of these little guys, we can choose a D module that has, if we look at sort of like going around one of these guys in a circle, we can choose a D module that has a different, so from this path around this puncture point, we can choose a vector space that changes in some way via some linear transformation when we go around this path. And so for every one of these points, we can choose an invertible matrix. And if we choose a different one, we're going to get a different D module. So roughly this is kind of how it works. But it is different. So there's sort of processes we can like D modules can be constructed in lots and lots of ways. The takeaway is just meant to be that there are many D modules. Awesome, thanks for asking. Any other questions? I meant to say this at the beginning, that I very much welcome questions, and so you can stop me at any time. So this is the end of our historical bit. So the takeaway from that is that this is a theorem that is not exactly new. It was proven in 1981, but I find it so beautiful because it marked a turning point in the way that we look at problems in the field of representation theory. And how it shapes my mathematical world personally is that I study representations of Lie algebras. And I'm interested in representations of Lie algebras that are not in category O. So I like to study these representations called Whittaker modules. And I like to think about these things as living inside some category called N, which was introduced by Milicic in Zorgel. And these representations are kind of wild. For example, they have no weight decompositions. They're not weight modules. But because Beilinson-Bernstein's theorem applies much more generally than category O, we can still take their localization and we can think about them as D modules. And it turns out that the D modules we get are these exponential D modules. And these are also kind of wild. They have irregular singularities, but there are more tools, and they're not so wild. They're still a reasonable class of D modules that we can study. So from my perspective, I like this theorem because it just gives me a set of geometric tools to think about these representations of Lie algebras that I care about. Yes, they are. Thanks, Monica. So there's still D modules on G mod B, but they're, well, hopefully if I go fast enough, we'll get to see an example of one of them at the end of the talk today. Okay, and now we're getting to the point that we want to get to, which is the plan for the rest of the talk is supposed to be lots and lots of examples. So what I want to do is I want to show you what some of your favorite representations of SL2 look like in the clothing of D modules. And so from here, we're going to switch gears. Up until this point in time, I was kind of vague, showing you history, and now I want to get very concrete. So for the rest of the talk, I want to have concrete calculations, and my goal of this bit of the talk is to convince you that D modules are simple and reasonable objects to work with, and they're a nice way to view representations. So for the rest of the talk, we'll work exclusively with the Lie algebra SL2C, and this is what our geometric picture looks like. The flag variety, in this case, looks like P1, which I'll think about as a sphere, and I'll label the North Pole 0 and the South Pole infinity. And what I'm going to do for the rest of this talk is I'm going to do algebraic geometry very concretely. So there's some argument that maybe this is not the best way to think about algebraic geometry, but I like to think about it in terms of charts. Think about it. I'm going to tell you about sheaves, and I'm going to tell you about sheaves by giving you open sets on my variety and telling you what vector space to assign to each open set and how we can glue everything together. So I need some charts. So on P1, I'm going to cover it by two charts. The first chart is what I'll call C infinity, and it's called C infinity because it contains infinity, and it's everything except 0, so this looks like a copy of C. My second chart is the opposite. I'll call it C0 because it contains 0, and it's everything except infinity. It looks like another copy of C. So we can cover P1 with these two charts. And then our starting place, I want to describe to you D modules. And so these are going to be sheaves of modules, but what are they modules over? They're modules over a ring that's captured by this sheaf of differential operators. On X. And now how we think about this? Well, this is just described by the data of two rings.
Anna, quick interruption. There's a question in the chat. They're asking, do the D modules corresponding to Whittaker modules have regular singularities?
No, they have irregular singularities. Yes. This is why I describe them as wild. And hopefully we'll see an example of one at the end. And so you'll be able to see what it looks like to have irregular singularities and kind of what this means. Thanks. Okay, so how are we going to think about the sheaf of differential operators? Well, this is really just the data of two rings. The first ring is what we get if we look at the ring corresponding to our C0 chart. And this is a ring of differential operators in one variable. So it's just generated by multiplication by z. I'll choose this as my variable, and differentiation with respect to z, subject to the relation that if we take the bracket of dz with z. By bracket, I just mean the commutator. This should be equal to 1. So this tells us, so this is a non-commutative ring, and this tells us that we can move z past dz at the cost of a -1. And so this is the ring that we get corresponding to this chart. And then we also have a ring corresponding to the other chart, W, dw. And this is subject to the same relation. And the way this is a sheaf is that these things are glued together by the relationship that our variable on the second chart is the inverse of our variable on the first chart. So I will be describing D modules, and they will be modules over one of these two rings. And so just a quick remark. In the statement of the theorem that I gave you earlier, there was a twist showing up. So in Beilinson-Bernstein's theorem, the infinitesimal character of the representation of the Lie algebra is reflected geometrically by a twist in the sheaf of differential operators. And for the purposes of this talk, I'm going to ignore the twist. In this talk, I will ignore the twist. And all this means is I'm focusing on the case of representations of infinitesimal character that's the same as a trivial representation. So trivial infinitesimal character. And the reason why I'm doing this is because the twist doesn't really change the structure of the D modules very much. The D modules that I'm going to show you will have basically the same structure. What do I mean by twist? Good question. So what I mean is that this here is a sheaf of differential operators, meaning that I get a ring for each of the charts and there's glue. I could glue this together in a different way. So if I have a sheaf of twisted differential operators, it's a sheaf that locally looks like a ring of differential operators, but it's twisted in some non-trivial way. So we can somehow use lambda to construct a sheaf that locally looks just like this one, but there's sort of some gluing that makes things a little bit more complicated when you move between charts. But locally it looks the same as one of these sheaves. And so the structure of the D modules is essentially the same, but the formulas come up with a bunch of twists, which just makes them a little bit harder to write down. So I'll try to keep things a little bit cleaner today by ignoring the twists. But I will say that if you're interested, so I should say that ignoring the twist just means that I'm considering just representations. So work with infinitesimal character 0. But the story with twists, if you want to read about it, I wrote it down carefully recently. So the story with twists can be found in this note on my website that's called 4 Examples of Beilinson-Bernstein Localization. So if you want to see the whole story, take a look at that. But for today, it'll be a lot cleaner if we ignore the twists. Great. So what I want to do today is draw D modules. So what does that mean? How do you draw a D module? Well, this is the way that I'm going to do it. From our setup, we have this tower of inclusions. So we have up top, we have our flag variety. On the sides, we have each of our 2 charts where we take away 1 point. And then down below, we have the intersection of those 2 charts, which looks like a copy of C star. So the way I'm going to draw D modules is I'm going to describe them by giving you the following pieces of data. I'll start by giving a vector space for each chart. So I'll call this MC0 with an action of the ring Z dz. So this was the ring of differential operators associated to that chart. And then I'll also give you a vector space MC infinity with an action of the other ring of differential operators, which was just in terms of W's. And then I'll tell you about the restriction maps. So I'll put these 2 vector spaces into a diamond where I have one of my D modules over here, the other one over here. And then I can look at what this sheaf looks like on the intersection of these two things. And I'll describe how we restrict from C0 to the intersection, and how we restrict from C infinity to the intersection. And the reason I'm describing this way is because, remember, my goal is that I want to describe the global sections of a D module. And I can compute this using these three things. And so the way I can do this is that the global sections, in terms of this data, are going to be given by pairs M and N, where M is some element of the vector space MC0 or MC infinity, and these are supposed to be curly M's, and N is some vector in the vector space MC0. But they give us global sections if they have the property that they restrict to the same thing in the intersection. So the restriction of M is equal to the restriction of N. And so this will let us put a third or a fourth thing on our triangle to turn it into a diamond. And so I'll think about the global sections as here living up top. Okay, so this is my procedure for how I'm going to draw D modules for you. But there's one last thing I have to tell you before I start actually doing this, which is how we can see them as representations. Because I don't want to just think about the global sections of D modules as a vector space. I told you earlier that these things should have the structure of a representation of a Lie algebra. So how does this work? How do we realize global sections as representations? Well, the starting place is that our flag variety isn't just a variety. Well, it is a variety, but it has this underlying group action because it's defined as a quotient of the Lie group corresponding to our Lie algebra. So we get an action of the Lie group SL2C on our flag variety. And this action I'll think about as follows. So if I have some matrix A, B, C, D in SL2C, I'm going to think about points in P1 as lines in C2. So this is a line in C2 through the point XY. And this action is just by matrix multiplication. So AX plus BY, CX plus GY. Okay, so we have a group acting on a variety. And from this, we can differentiate. And this gives us a map from the associated Lie algebra, SL2C, into vector fields on P1, the Lie algebra of vector fields. And so these are derivations, so they're first order differential operators. So we can think about these as living inside of our sheaf of differential operators. So by differentiating this group action, we should have some way of taking an element of the Lie algebra and coming up with a vector field. And this is actually something we can compute. We can compute this. So I'll give you one example so we can see how it works. So if we look at the standard basis for SL2, oh, I changed how I'm going to do this in color. These colors are not just random, they will stay throughout the talk. So we can write everything in SL2 as a linear combination of E's, which will always be green, H's, which will always be orange, and F's, which will always be blue. And let's look just at one of our charts, our C0 chart. Remember, this is the chart that contained zeros, so it looked like this. We could think about this as lines that are all of this form, where we can scale the first coordinate to be 1 and the second coordinate we're going to call Z. and this is isomorphic to C. And then if we look at some C infinity function on this chart, then what this differentiation looks like is the following. If we want to see how the Lie algebra element E acts on this function f of z, this we can find by the following formula. We differentiate and evaluate at 0. What we get if we exponentiate the Lie algebra element with a t, this gives us an element of the Lie group, and then we act on the function. So let's go ahead and do this computation. So the first step is, what is the exponential of TE? Well, this is just the Lie algebra, or the Lie group element, 1, 1t. And now we want to use this to act on this function on C0. Well, we know how the Lie group acts on the variety, and so the way that it will act on functions is by acting on the inside of the function by an inverse. And so we can look at how this matrix acts on something of the form 1z. So we'll do this maybe on the side. The inverse of the matrix is 1, negative t, 0, 1. How does this act on 1z? Well, the formula over there just told us that this should be 1 minus t and z, 1 minus tz. We can scale to write this as 1, oh, sorry, this is kind of a mess, 1z over 1 minus tz. And so this tells us that this action looks like precomposing our function with z 1 minus tz. Okay, and now we should, in theory, be able to take some derivatives. So if we take this derivative, we're going to get f prime of the inside multiplied by the derivative of the inside. I really shouldn't try to do any sort of computations live. This is a bad idea for me, but I started, so keep going. Hopefully this is okay. Evaluate this thing at t equals 0 and do some simplification.
I missed when the t became a minus t.
Oh, because I'm acting on functions, and so I'm acting on...
Okay, got it. I think you said that. I just was scribbling something. Thanks. Okay, sorry.
No problem. Thanks for asking. So if I did this computation right, which my notes seem to indicate that I did, if I do all of this, if I do this derivative, evaluate at 0, I should get z squared times the derivative of the function I started with. And so what is this telling us? What was the point of this computation? Well, this tells us that in the chart C0, the Lie algebra element E acts by the differential operator, which is take the derivative and multiply by z squared. So this is some differential operator that is now going to show us how the Lie algebra element E acts. Okay, so the point of this was to show you that this is the computation that we can do. Like, we can figure out what differential operators correspond to Lie algebra elements, and it's kind of fun. If you like this sort of thing, you can keep doing the rest of the Lie algebra basis elements, but I'm not going to do those live. But by similar computations, we can get some formulas that look like this. And notice that I had to do it in each chart. So there's a different formula in each chart, because in each chart we have a different variable. And so this tells us here in the C0 chart exactly how our Lie algebra acts, and in the C infinity chart exactly how our Lie algebra acts.
And a quick question, I don't know if you've seen it in the chat. Monica is asking if it wouldn't be more natural to consider PLG instead of SL.
Oh, why do you say so, Monica?
Oh, just like acting on projective space in terms of like when you scale both points by the same scale, you get the same point. And so I feel like PGL versus SL works better with P1. But I mean, they have the same Lie algebra.
Yeah. Good point. I hadn't thought about that actually.
Okay.
Maybe. I mean, I assumed that you would get, since they have the same Lie algebra, you should get the same formulas, but maybe they're easier to compute.
Okay.
I don't know. I'm gonna try that sometime. I hadn't thought about that. Good question.
Yeah, I only put it in the chat and didn't bring it up because thought it was kind of a minor, possibly technical thing.
Yeah.
Okay, thanks. All right, sorry to interrupt.
No
Thanks
problem.
for too.
Okay, so, oh, I'm going too slow, so I should go faster. So at this point in time, what have we come up with? We have these formulas, and these formulas are useful because they let us describe D modules even more explicitly. So earlier I told you we were going to describe D modules as vector spaces with these actions of differential operators, but now we can describe them as a collection of vector spaces that have actions of a Lie algebra as well. So let's get to our first example. Also, I should, Nicole, will you give me like a time warning at some point in time when I'm going too slow? Like when I have like 5 minutes left?
You have 10 minutes left.
No, I'm too slow. Okay. So we'll see at least one example, and then maybe I'll show you some pictures of other examples. So let's go through this example carefully. We should get to at least one example. In the seminar,
we can give you like 5 more minutes if you need them. It's fine.
Okay. I've only been giving 2-hour seminar talks lately because for some reason this is like the standard in Australia. All of our seminars are 2 hours, and we always have 2-hour seminar talks. And so I've gotten used to too long of ones. But let me say more things instead of saying that. So I built up all this machinery because I'm supposed to be telling you some examples. So let's try to do one. So here's a first example. A sheaf of regular functions on P1. This is supposed to be a D module. So what is it going to look like? Well, I told you I'll describe it in terms of this diamond. So the first thing I want to do is look at what it looks like on the C infinity chart. So these are just functions on this copy of C, which are polynomials in the variable W. And we can draw them as a picture. So these are spanned by monomials, 1, W, W squared, etc. And then over here, I copied my collection of Lie algebras, or Lie algebra elements and how they act, so I can remember this, and we can write down these formulas for what this thing looks like as a module over the Lie algebra. So what does the difference, so we're working in the second chart, working in C infinity chart here. So E is supposed to act by differentiation with respect to W. So that means that if we act on 1, it annihilates it. If we act on W, we should get -1. So this is taking W to -1. If we act on W squared, this is going to be -2W, and so on, -3. Okay, so that's how E acts. Now, what about F? F is supposed to act by W squared dW. So again, if we act on 1, we're going to annihilate it because the dW is here on the right, so it'll kill 1. If we act by W, then we should get, so we'll do one of these computations slowly, maybe so we can see it. So if we have W squared dW, and we're acting on W, well, this just gives us, I want to act on, oh yeah. This gives us dW annihilates W, and then we're left with 2 of these, so we get W squared. So this tells us that we should have a 1 right here. And if we keep doing these computations, we're going to see that this is a 2. And how does 1 act? Again, we have H acts by -2W dW, so it's going to annihilate 1, but it will send W to -2 times W. It'll send W squared to -4. And if we were to keep going, we would see that this was going to be a -6. Okay, so all these arrows, all I'm doing here is I'm just applying these formulas of differential operators to polynomials in the regular way that we would think about differentiating polynomials. And so this tells us in this chart what it gives us a vector space. It's a vector space that's a module over this ring of differential operators, and it's a module over the Lie algebra. Now, what about the other chart? In the other chart, OX C0. Well, this is supposed to look like polynomials in the variable Z. And so again, I'm going to draw a picture of it in the same way. So we have 1, Z squared, Z cubed. And if we write down our formulas, I won't do them live, we're going to get a picture that looks something like this, 3. If you're bored, you should do some of these computations yourself sometime. They're kind of relaxing. -4. And again, we'll see that this, this H operator is going to act on each of our monomials. They will be eigenspaces for this operator. Okay, so this gives us my 2 vector spaces. And I told you that I was going to put these into a diamond to tell you about the restriction maps. And this was our last step. So if we look at functions on the intersection of these are regular functions on C star. And so these are going to be polynomials in Z and Z inverse. And so I can draw them as something like this. See the inverse, see the -2. And again, I already computed these formulas. So if I do them again, they should look the same. We should have our elements E are always going to be knocking us to the right. And the pattern looks something like this. Our elements F, look something like this. 1, 2, these are just the same arrows that I had above, but now they can be applied to something that's a polynomial in both Z and Z inverse. -2, -4. Let's move this guy up a little bit. Okay, so we have the starting bit of the data. The last bit of the data are what these restriction maps are when we go to the intersection. And in this case, these are both just going to be inclusions, because polynomials in W are in particular polynomials in W and Z, and same for polynomials in Z. And so then what I told you before is that we should be able to use this to find the global sections. And so the global sections of OX, these should be pairs of a polynomial in W and a polynomial in Z, with the property that they restrict to the same thing, but restriction is just inclusion, and so that means they should be equal. And so global sections are pairs of polynomials in Z that are equal, or pairs of one polynomial in Z and one polynomial in Z inverse that are equal. This can only happen if our polynomials were constant to begin with. And so the global sections are exactly the constant functions. And I've told you a little more in all these pictures by drawing all these arrows. I've told you how the Lie algebra acts. And so if you look at the ones showing up here, all Lie algebra elements kill 1. And so E acts by 0, oops, F acts by 0, and H acts by 0. So what representation is this? It's not particularly interesting, but it's a one-dimensional representation. It's a copy of C, where all of the elements of the Lie algebra act by 0. And so this is just a trivial representation of SL2C. Great, so this was our warm-up. We got some more work to do. But if we take the first sheaf that I told you, the sheaf of regular functions, this has a natural action of differential operators, so it's a D module. And I've described it by telling you super explicitly in each chart what it looks like as a representation of G. And its global sections are exactly constant functions with a trivial action of G. So this gives us the trivial representation. Okay, so maybe this wasn't the most interesting example, but we have many more. Oh, I'm too slow. Okay, I catch some of the things. So let me tell you, so maybe I'll go 5 minutes over and I'll try to do this example carefully, and then I won't get to my last 2 examples. But you are welcome to look at them in my notes, or I could just, yeah, the pictures are there. So how else are we supposed to build D modules? So far I've built a D module by kind of telling you about a sheaf of functions, which is naturally a module for differential operators. But it turns out we can also build D modules using stratifications by group orbits. So if we look at the subgroup of SL2, which is these unipotent matrices, this acts on P1 in the same way that SL2 did. And if we look at the orbits under this action, we're going to get 0 will be fixed by this. And then we'll get another orbit, which is everything except 0, which is our chart C infinity. So from these orbits, we can build D modules in a pretty natural way. And to do so, we can look at, remember the structure sheaves are kind of our first class of D modules. So if we look at the structure sheaf on an orbit, this is a module for the sheaf of differential operators on that orbit. So that gives us a D module on a subvariety. And then we have all of these pushing and pulling functors. So we can push forward along the inclusion of the orbit into X. And we can build a D module, I plus, by pushing forward this structure sheaf on the orbit. And this thing, darn it, is a dx module. Okay, so how does this work? Let's try it on these two orbits. So we have two orbits here, a closed orbit and an open orbit. And so the first thing we can look at is what the D module looks like if we start out with the structure sheaf on a point and we push it forward. So our first step is we need to look at what the structure sheaf, what O point looks like. And this is just a sheaf of functions on a single point. And so this is just a copy of C. And this is supposed to be a module for differential operators on a point, but that's also just a copy of C. And so on a point, it's pretty simple. And what happens when we push it forward? Well, if we push forward this D module, what this is going to look like is it's going to be this span. It's going to be a D module that's supported at this single point because the point is closed. And so when we push it forward, we can only change, the push forward can only change the support of a D module to its closure. So if we start with something closed, it still has to be supported on the closed thing. And so what this looks like is the span of the Dirac delta function. So this is some function that integrates to 1, but is supported just at a single point. And if we act on this guy by z, we get 0. And so here, this is going to be a D module, but if we look away from 0, it's only supported at 0. So if we look at any chart that's not containing 0, this D module is going to be 0. So it's only supported in our C0 chart, since that's the one containing 0. And I think, instead of drawing this, I think I have it later, right? This is what I'm gonna do. Sorry for the scrolling. I already did it. I can copy things. So here's a picture of the diamond for this guy. So this is what we called M point. So from this diamond, because our D module is supported on a single point, if we look at the chart away from that point, we just have nothing. And if we look at the chart that includes that point, then we have this funny D module, which is just a span of this Dirac indicator function. And as a D module, when we act by z, we get nothing. And when we act by partials, we get different elements in the D module. And again, if we look at the intersection, this doesn't include the point that this D module is supported on, so it looks like 0. And so this D module only exists here in this one chart. And if we write down the action, again, of our Lie algebra is now working in the 0 chart, so if we write down the action of these Lie algebra basis elements on here, we can do the computations and see that as a module for the Lie algebra, it looks like this. These are the actions of the Lie algebra elements. And so then if we want to look at the global sections here are going to be pairs, 0, and some vector in here that both restrict to 0. But this we can just identify with a vector in here because everything's going to restrict to 0. So the global sections here look like this chart here. And what does this look like as a G module? If we stare at it for long enough, which I certainly haven't given you enough time to stare at it for long enough, this should look somewhat familiar, at least the way I've drawn it. It's a weight module because H acts by, well, we have written it as in terms of a basis where H acts by scalars. And so with a few change of bases, we could see that this thing here is an irreducible Verma module. And it's of highest weight, -2. Okay, so this process has given us, by taking a D module on an orbit, the closed orbit, and pushing it forward, we ended up with a D module whose global sections look like an irreducible Verma module. Great. Oh, I really didn't time this well. So I have many more examples, which I'm not going to have time to show you, but maybe I can at least show you the pictures so I can get to the punchline of.
So Anna, just so what we can do is we can thank you, and then afterwards, after questions, if people have questions, then we can, after the questions, we can spend more time and calmly go through all the examples if you'd like, because I would personally like to hear them. But just for recording purposes, I don't want this to be a 2-hour recording. So, and then
Okay.
if you have the time and you'd like to spend an extra 30 minutes or however long you need explaining the rest of the examples, that would be fantastic.
Yeah, I'm happy to. Okay, so maybe I'll give a bit of a summary now for those who want to leave after an hour, and then if people want to stay, I can keep going. But I should say that it was very rude of me to be so off. I'm sorry that I was so completely off with my timing. I always forget how long it takes to compute these examples. But let me say the punchline of at least this bit of the example. What I was trying to get to is that I've told you now there's supposed to be 2 orbits. I've told you how we can build a representation from this orbit. If we did the same process with the other orbit, if we started with the structure sheaf on this orbit, pushed it forward, looked at its global sections, we would see that we also got a module that looked sort of like a Verma module, that it was going to be a dual Verma module. And from this procedure, we would get all of the simple building blocks of the principal block of category O. So these D modules that correspond to stratification by n orbits, these things give us irreducible G modules and Verma modules. And then the other examples I'm going to get to are stratifications by orbits of a different group, which will give us representations of the Lie group SL2R. And then last, I was going to talk about Whittaker modules, which are constructed in a different way, not quite by these stratifications. So if you have to leave and are interested in the pictures, they're all in my notes. If you want to stay, I'll keep going. Thank you so much for having me, people.
All right, let's thank our speaker. Are there any questions for Anna about anything she's covered so far?
So thank you for a great talk. So I just have a question. Just I forgot the kind of how the correspondence goes. So you need to go from, when you go from modules over the algebra to D modules, you need to tensor some kind of bimodule that is sort of a module over universal developing algebra and the sheaf of D modules, but I forgot what it was. But
oh, so you're asking about the localization functor, what it does?
Exactly.
Yeah, okay. Well, yeah, you got lots of room. So this localization functor from G mod to D lambda mod is we take some G module, X, and we send it to, so we take this as a module over what I'm going to call U lambda. And so for our choice of lambda, lambda is something in the dual of the Cartan, we have the corresponding infinitesimal character, which is a map from the center of the universal enveloping algebra. And then we can look at the ideal generated by the kernel of this guy. And well, actually, U lambda is just the quotient of the entire universal enveloping algebra by the ideal generated by the kernel of this. And then any module that's a G module of this infinitesimal character will be a module over this algebra. And then we tensor this with D lambda. And so we can think about this quotient of the universal enveloping algebra as living in the sheaf of differential operator, one of these twisted ones. So this is how we can give a modular structure. Is this what you were asking?
Yeah. So D lambda is a particular sheaf that is above. So it's a D module and a module over U lambda, and the 2 actions commute, or sort of, I don't know. But D lambda, for the trivial cases, D lambda is to describe. For the untwisted case.
Yeah, for the untwisted case, this is just dx, the sheaf of differential operators. And this quotient is just the quotient of the universal enveloping algebra by the center, but with pods. So like this is a polynomial algebra. So if we look at U0, we look at the UG quotient out by the ideal, which is just CG plus, so all the positive degree things. Then this is the, yeah, that's the U lambda that shows up in this trivial case.
And somehow this functor is exact because of some property of restriction of d lambda on suitable open sets. Like, I guess it's some, I remember, but it's an exact functor, so it's
yeah, it is exact.
Of d lambda, maybe being a free module, or like if you restrict unsuitable to a G-invariant open set, or sorry, I guess I'm not making sense.
Yeah, no, you are making sense, but I'm not quite sure the answer. I don't remember why it's exact.
Thank you.
But it definitely is, yeah.
So I had a question about unitarizability. Is it easy to say what structure on the D module side corresponds to something like unitary structure on a irreducible representation of a real group?
I think that this is exactly the stuff in Valonen's recent work, but I don't really understand it personally. So my last example I was going to get to is I was going to describe some D modules corresponding to admissible representations, and then I can tell you for SL2 which of these admissible representations are unitary, but it's not obvious to me what structure in the D module describes this unitarity. But I think that but in this recent work by Valonen, I think he has a description in terms of like Hodge filtrations that sort of tell you. But I would also like to answer that question.
Okay, all right, thanks.
I'm sorry, may I ask you, how do you push forward the D module? Could you be more specific how you pushed it from the North Pole?
Okay, so in general, what you need to do is so it's generally like a process of by tensoring with this this D module that sort of moves us from, okay, let's see, I can just write it down. I point plus is of whatever we're pushing forward. Is if we take our module here, and this thing is in particular a module over O of a point, and we have sort of this transition D module which takes us from modules from X to the point. And then we can write down, let's see, what does it look like in this example? So, I'm not answering this particularly well. So maybe, so I've gotten a little confused. So this guy, so each of these is going to be oh no, actually this should be D. So there's a procedure by taking a D module. So the push forward is like a little bit complicated for D modules. We start out with our D module on whatever the subvariety is. And then there's this transition module which lets us, which is a left module for whatever the map is here. So whatever the bigger space is, and a right module for the smaller space. And this lets us transition the D module structure on the point here to a D module structure on the entire, for the entire sheaf of differential operators. So this thing has an action of dx. And then the question is how this is defined. And this is the part that I'm not quite remembering at the moment. But I think, yeah, if you stick around for my next example, it might be a little bit more obvious. It's a little strange in this closed point example because it's so small. But one other way we can think about this, this D module, instead of just being the span of this Dirac delta, is as the sheaf of differential operators on whatever our C0 space is, where we mod out by GC, I think. Sorry, this was not the most satisfying answer to that question, but I can, yeah.
Can I ask a different question? In what sense is this a Dirac delta? Or like, what does that integral sign mean?
Only vaguely. So if I were to integrate this over, so now I'm thinking about this, if I draw it in this picture, I'm thinking about it as on C. So, so this chart looks like C. And so as a function on C, it integrates to 1 and is supported at a single point.
But I mean, it's not actually a function, right? It's like an element of I guess I'm asking, is there a way to make sense of integration generally in this context?
No, I guess just formally this is an element that, yeah, maybe integration is not the best way.
No, I mean, it's suggestive. I like it. I mean, it makes sense because it is a function on the point and you're pushing forward. Thank you.
Anna?
Yes.
So like here, you recovered the Verma module m-2, and -2 is like the S dot action on 0.
Mm-hmm.
So like what happens in general? Like, so if you have like G mod B and you stratify and you take push forward of like let's say what's it called like
you get the Verma corresponding to the lowest W in your orbit. I think this is answering your question.
Okay. Yeah, exactly. Okay, thanks.
Yeah, so the D module supported on the, so in general, you'll have G mod B and its stratification will be given by Schubert cells, which are parameterized by the Weil group. And you will get the irreducible Verma module in that corresponding block of category O. Does that answer your question, Caroline?
Yes.
I'm sorry, could you say something how you push forward from the other orbit, the open one?
Yeah.
Sorry.
I think this is what I'm going to do next, if you can hang around for a little while longer. I was going to get to the open orbit in my next example, and so maybe if you can stay for a few more minutes, I'll do that carefully.
All right, in that case, let's thank our speaker again, and then I will stop the recording and we can continue with all of your examples. Thank you, Anna, for a wonderful talk. Thank you for coming. And just before we quit, next week we'll be back at the usual hour, not at this later hour that was Sydney time. So keep posted and see you guys next week. All right, I'm going to end the recording now.